Okay, today, inshallah, we'll take lectures for decoders and multiplexers. We'll study how decoders and multiplexers are designed in computer hardware. So we will cover this week. We will cover decoders. We will cover encoders. We will cover also multiplexers and demultiplexers. So we'll talk about decoders and how they are working, and then according to decoders, we'll take multiplexers because multiplexers are an extension of decoders, and then we study encoders and then demultiplexers. So the main idea of any computer system is just to have a memory, and this memory contains instructions like data, like instructions or code. They are all represented in binary. They are all represented in binary. And we have the CPU. The CPU contains two main parts, the control unit and the arithmetic logic unit. We can see that control unit, for example, has a data path. This data path, we will see how it is represented in computer hardware. So the control unit has a data path unit, and the data path unit is like the corresponding arithmetic logic operations. It's doing the arithmetic logic operations. How the data path represented the arithmetic logic operations? Okay, I will see that in the next slide. What about the control unit? The control unit sending the control to the data path to provide the corresponding operation. For example, if I want to make addition, so control unit will initiate addition. If I want to make subtraction, so control unit will send subtraction or control signal that enable the subtraction circuit and so on. But how to do that physically is just to use multiplexers. So if you see this is a CPU data path, it will be like that. If you look to the details of the internal structure of each one of these, I just want you to, okay, let me explain it by the annotation. Okay, let me explain it in just a simple example. If you look here, we have register 1 or register 0, register 1, register 2, and register 3. Okay, these registers are the registers of the processor. And we want to make, for example, I want to add the contents of this register to that register. I want to add them, addition, to make addition. And pass the result to R0. So I add R0 to R3 and then put the resulting value to R0 again. Okay, this is an example just to show you the how what is the meaning of data path. So now we should have a multiplexer, and the multiplexer is selecting which register will be enabled. According to this, the value of R0 will be passed to the output here. This is R0. Because we know that multiplexer will enable this R0. Because I need R0. And I need R3. Also, I think this is not going to work. Yes, R3 is passed to multiplexer, the other multiplexer, and because we have a connection here, if you see, so the output will be on that path. So here we will get R3. We will get R3. Okay. Now we have R0 here and R3 here. They are because of the multiplexers, we select which register we want to work with. According to which register we want to work with, we are using multiplexers to select which multiplexer we want. Now we have the values passing to another multiplexers, or you can say, just to ignore this part, just passing to the arithmetic logic unit. We want to make what? We want to make addition. So the arithmetic logic unit will do the addition, and the result will be, if we want to make shifting or something, so we pass it by shifter unit and return it back to here. But anyway, don't concentrate, just ignore this part now. I want you to know how multiplexers are used, just to select the registers, and then according to the values passed to the arithmetic logic unit, we will do the addition, and then the result will be back again to the registers. If you see, this path is back again to the register. The data will be passed to the register according to a signal from what? From the decoder. So that's why we need a multiplexer, just in selecting which register to be used, and the decoder to enable which input I want to enable. I want to enable this input, so the decoder will decide which enable will be used, which signal will be used, or which register will be enabled. Okay, this is just a simple example to show you the importance of decoders and registers in the processor or any electronic circuit, in any control circuit, not just a control circuit, contains CPU and contains memory. Okay, so we have registers, we have multiplexers to select which register. We have four registers here. So the data will be passed according to which register I want to take. So the data will be passed here, and this multiplexer will select another one, and accordingly we select which data. For example, here we have a constant, we have the input here, so it selects which data. I want the constant or I want the value from the register. Accordingly, I will select from using this multiplexer, and the decoder will enable which uh, register to load back the result. Okay, so the decoders and the multiplexers are important ourselves. And we want to concentrate now on the decoders, how the decoders are working. So, for example, if we have four devices here and the devices are connecting directly to a specific bus, I want the control unit to just enable only one device at a time. I want to have only one device at a time to write on the bus. I need only one device at a time to work on or to write on the bus. Not all of them. I want one only because it is only one bus, and I want that bus to carry only one value at a time. For example, if device 0 is writing to bus, okay, let me see the chat. Yes, I'm recording. I'm recording okay. I'm recording, no problem. I'm sure. I'm recording from the first, from the beginning of the lecture. Yes, okay. Okay, thank you. The control unit here want to enable which device. I want to know which device uh, to be used. Okay, I have to find a circuit in between here. This circuit is enabling one of the device at a time, not all the devices at the same time, only one device at a time. So we enable this one and disable that one, disable that one, disable that one, for example. Okay, I want that device between the control unit. I want a circuit here. This circuit is a decoder. And this decoder is 2 to 4 decoder. 2 to 4 decoder. The simple truth table is like that. If we have A1, A0, 0, 0, 0, 1, 1, 0, 1, 1, and in each selection of these, we have only one D is enabled at a time. So here we have for 00 we have D0 is active and the others are not active. The 101 we have D1 is active, the others are not active. 10 is here, D2 is active and the others are not active. And the one here, the same thing. So we will have one active line at a time. For example, here if we have 00, so this line will be active. So device 0 will be active. If we have 1010, so this device number 1 will be active. If we have 01, we will have device 2 will be active. And if we have 11, device 3 will be active. And the others will not be active. Okay, this is the main concept of the decoder. So it is just describing this way. We have D1 is active at the time because we have 10, 10, we have 0100. So this device will be active and it will write on the path and so on. Okay. So how to implement this circuit? How to implement it? We have a logic of A, and this logic is uh, just a simple signal. This signal is converted to D0 or D1. This is the simplest one, which is the uh, just single input, two output, 1 by 2. This is 1 by 2 decoder. This is very simple decoder. The 1 by 2 decoder is the just invert or the complement of A and A itself. So the complement of A will be D0 and A itself will be D1. And the truth table of this very tiny circuit here, which is A is input 0, the output will be D0. If the input A is 1, the output will be D1. So it is very simple. Okay. What about this one? This one is very important because you are going to use it many times. How to implement it? How to implement its logic? The logic circuit. I want to know the shape of the logic circuit. I have to check the truth table, and accordingly, we will have 1 with D0, which is equal to 1 only at A1, A0 equal to 00. So if you see here at D0, D0 will be active only if A0, A1 is 00. So 00 here will be converted to 1. So this will be enabled, and this will be 1, and also this will be enabled, and others will not be enabled. So D0 will be active if A0, A1 equals 00. Okay, this is straightforward. I think you understand it. For example, if I want to represent the D3, D3 is A1 equal to 1 and A0 equal to 1. So D0 is like getting not converted values of A0 and A1, as you see here. Okay. So this is the decoder and this is the circuit of the decoder. We have two input, and according to the value on the input, the corresponding line will be enabled and the others will be disabled. Okay, I think. Okay, let me repeat it again. Okay. So, for example, if the input is 00, the D0 will be active. Yes, this is D0 because it is A1 complement, A0 complement. And about A1 is 0, so D1 will be active, which is this one. And A1 A0 is 10. This is D2 will be active, and the others will not be active. And the final one is A1 A0 equal to 11. So accordingly, D3 will be active, the others will not be active, and that's it. Okay. They are, if you notice, they are a min terms. They are a collection of min terms. The min terms of these values. So we have uh, A1 complement A0 complement. We have A1 complement A0. We have A1 A0 complement. We have A1 A0. So they are the min terms. They are the min terms. They are the min terms. Okay. Because this notice is very important. We will need the min terms in the how to represent any logic using the decoder. The decoder can represent any logic you want. Okay, how to implement 3 by 2 decoders. If you want to understand the decoder, you can say if you study the conversion is just binary to octal, and we have the binary here, which is the three inputs here, representing binary value and the corresponding octal value at the output. Okay, so here, like having input in binary and the corresponding line will be active, the others will not be active. For example, if we have 0 0 0, this line will be active. If we have 1 1 1, the last line will be active and the others will not be active. Okay, they are the same concept of okay, let me, I have a phone call and I will be back soon. Okay, just a second. So here, the binary to octal is the 3 by 8 line decoder, and we have also the binary to hexadecimal values, like just a representation. If you want to remember the decoders and the name of them, to make it more, يعني, I mean, to remember it. Okay, so it is better to represent the 3 by 8 as a binary to octal, and 4 by 16 is a binary to hexadecimal. So you will not be confused about the number input and the number of the output. Okay, so we have these types of decoders: 3 by 2 and 4 by 16. The 3 by 8, sorry, it is 3 by 8. The 3 by 8 truth table is here, as you see. We have seven input from 0 to 7, and also the output, as you see, D0 is active. Only one line is active at a time. If the input is 0 0 0, the D0, which is the first line, will be active, the others will not be active, and so on. It's exactly the same circuit as the uh, the the 2 by 4 decoder, the same, no problem, no difference. Because they are the min terms, they are the min terms, and this is the implementation. It contains all the min terms at the output, and accordingly, if you have a value here, the corresponding line will be active, the others will not be active. Okay, how to make the enable? Oh yes, we have here, okay, we have here the 2 by 4. We need an enable signal. The enable signal is important, because if we want to have or to fix the value on the output to 0 0 0, all of them 0, because the we don't want the signal to be transferred from the input to the output. We want to stop it. So we need an enable signal. The enable signal needs another another four AND gates, another four AND gates. So they are not part of the decoder. You can say this is extra AND gates. These extra AND gates are used in enable or to make the enable signal. Okay, So if this enabled signal is on or 1 here as here, so all of the output is working normally, but if enable is 0, irrespective of the value of A1 is 0, the, the output will be all zeros. So this is the enable circuit. So if enable is, we have enable here, and this is, we need all of these and the gates. So if enable is 0, according to the enable is important, because if it is 0, the output will be 0 irrespective of the value A1 and A0. Whatever value of A1 and 0, the output will be 0. If enable is 1, this is a normal decoder. This is normal decoder. Okay. Um, how to implement a 3 to 8 decoder using two 2 by 4 decoders. This is very important example. This is very important example. You concentrate on this, because this is very good question. This is very good question. I have a 3 by 8 decoder. I want to have, or I want to realize 3 by 8 decoder using 2 by 2 decoders, uh, two copies of this 2 by 4. Okay, two copies of the 2 by 4 decoder. I want to have, or I want to represent the decoder of 3 by 8 using two copies of 2 by 4 decoders. How to do that? If you look at the 2 by 4 decoder, this is the 2 by 4 decoder, and according to the enable, okay, according to the enable, so I can make the enable, the last variable, as enable value. And the enable, this one will enable the first the first circuit if this is 0, and the second circuit, or the second decoder, if this is 1. So here we have A2 is representing enable exactly. Because if you see this, table is divided into two parts. The first part is 0, the second part is 1. So if the value is 0, we will working with A1, A0, but not two of them, but only one decoder. Because if this is 0, only that decoder is working, and that decoder will not be working. Then if we have this is 1, this means the A2 will be the control signal, and it enables that one, which is the second decoder, and it disable the first one, which is the first decoder. Okay, so this is how to represent 3 by 8 decoder using two copies of the 2 by 4 decoders. It is simple, because if I want to represent this logic, it is very straightforward, because A2 will be 0 and 1. It is similar to enable circuit. So whenever A2 is 0, one of the decoders is working. Whenever A2 is 1, one of the the other one of the decoders is working. They will not work at the same time. Okay? Okay. It has many applications, like octal to hexadecimal conversion, selecting memory banks. For example, four memory banks can be selected individually using two address lines. Implementing logic circuits, and we will see an example of implementing logic circuits. Decoders are used for microcomputer interfacing, for keyboard and display applications. As you see, as you know, that we have many input-output devices, and one of the devices will be active at a time, and this is only done using the decoders and multiplexers, which we will talk about later. So here the address decoding can be used using the 2 by 4 decoder as we have seen before. Okay. If you have any question in this part, you have any questions? Any question about decoders, multiplexers? Sorry, decoder, only decoders. Okay, I will ask a question to see if you are here and you are listening to me. Can anybody tell me the idea of the decoder here in this figure? Anybody tell me the idea of the decoder, how the decoder is working in this circuit? يا شباب حد معايا ولا ايه؟ بنات شباب حد معايا؟
معك دكتور.
طيب الموضوع بسيط. It's very simple. Okay, Abbas is sharing on the chat. He's saying 2 by 4 decoder using enable. Yes, I want to the idea of the decoder. I mean, we have memory banks here. I want this memory bank to pass the entire bank to the bus. So how to select which one? The idea. The idea of selecting one of these memory banks. Can anybody tell me? Explain, just explain as I'm a student and you are the teacher. I want you to explain to explain the decoder. Yes, Nurhan is sharing on the chat. She's saying to input have four output and one output will be active at a time. Exactly. Yes. Okay, that's perfect. So we have for two input here and for output, and one output will be active at a time. So this memory bank will be active only when this is 00, and this memory bank will be active only when this is 10, and this memory bank 3 is active when this is 01. Yes, 01, and then the last one is 11 when we have an input is 11, the last one will be active. Okay. And as Abbas Mahdi said, and he said that enable is important here because if we want to enable the entire circuit, we need the enable signal to enable the decoder. So we will enable it. We'll see one active device at a time. If we don't have enabled active, so there is no active devices. Okay. Okay, let me ask another question. Okay, this one is important. Can anybody tell me how to realize 3 by 8 decoder using two copies of 2 by 4 decoder? We have two copies of 2 by 4 decoder, and we want to use them to represent 3 by 8 decoder because the representation of 3 by 8 decoder is like this is most fit. Yeah, I mean, if you have two decoders of 2 by 4, you can represent 3 by 8 decoder. This is design. This is what is designed. Because if you don't have the 3 by 8 decoder and you already have 2 by 4, two copies of them, this is going to give us a two by 4 decoder. This is going to give the same functionality. Okay. Okay, I think we were wasting our time. Okay, now we move to the second part, which is logic implementation. How to make logic implementation using the decoder. As you see, we have the min terms here, and if I want to represent any function I want to implement it, I can have these min terms collected together and OR them together using an OR gate, and then I have the logic that I want. Okay, let's take an example. If I want to make adder, you know the adder? The adder, if I want to make addition, so I have sum and carry. The sum is the collection of the sum of the midterms, which is 1, 2, 4, and 7, and the carry is represented by the midterms 3, 5, 6, and 7. Okay, these are the sum and carry. I want to represent them using the decoder. How to do that? The decoder is just we need, because we have seven values here. We have from 0 to 7, so we need 3 by 8 decoder. This is the first step. Then the second step is, we know that the decoder is generating all the minterms. So it generates 1, generates 2, 4, 7, 3, 5, 6, 7. All of them are there on the output because we have, according to which input, one of them will be an input. And we choose which minterms we will collect to S and to C. And finally, we have an OR gate that will sum up all the midterms that we need. And accordingly, the sum will be what? The sum will be 1, which is this one, 2, which is this one, 4, which is this one, 7, which is the last one. And we OR them together. Yes, we OR them just using an OR gate with 4 input. And the sum is here, which is the sum of the the input, the sum of the input, just the sum of all of these values. So if this is 0, 0, 1, so the output will be 1 because it is the sum, okay? The sum of the binary value. And the carry is the main term, is the third main term, which is this one, the fifth main term, which is this one, sixth main term, which is this one, seventh main term is this one. Okay, so accordingly, we will take an OR gate and have a carry. So now we have implemented an adder using decoder. So if a question happen in the exam and asking you to implement a logic gate using the decoder, you have to understand how to implement it. Okay. Another example, if we want to have this functionality, which is A complement B C dash D, and also the other one is A complement B complement C D, A B C D. I want all of these to be represented. We have the midterms, which is 3. This one is 3, 5. This one is 5, and 15. This one is 15. Now we need 4 by 16 decoder because we have 4 variables. So we have 4 by 16 decoder and select the midterm is 3, which is this one, 5, which is this one, and 15, which is the last one. Collect them together with OR gate to obtain F1. This is the function. Okay. Now you have to understand that we can use decoders to represent any logic we want. The encoding is the opposite of decoding. The encoding is the opposite of decoding. So if we have data lines as input, we will, I mean, if we have data inputs, the data lines as input, if the first one is active, the output value will be 0, 0, 0. If the second one is active, the output will be 0, 0, 1, and so on. So if D0 is active, the output will be, it is the opposite operation of decoder. So this is the circuit of the decoder, and this is the encoder. Sorry, not the decoder, encoder. This one. So this is the circuit of the encoder, and this is the truth table of the encoder. As you see, we have represented A2 by this OR gate, A1 by this OR gate, and A0 by this OR gate. It is straightforward because I know that A2 is uh, that value, which is D4, okay, and D5 and D6 and D7. So if A2 is represented by what? These four, which is this is 7 6 5 4 4 5 6 7 4 5 6 7. Okay, just remember them. 4 5 6 7. We go up here A2, and then we will see that's 4 5 6 7. Okay, as you see, we will not use uh, the first line, which is D0. We will not use it either in A2 or A1 or A0. It is not used. So here we will not find D0. No D0 here. Why there is no D0? Because either A2 or A1 or A0 using D0, because they are all zeros here. There is no one here. But all the other values has one. This is A0 has one, A2 has one, A1 and 2 has one, and so on. All of them has one. But here there is no need for D0. That's why this circuit doesn't have D0. Okay? Okay. This is the main terms, and he just describing how to get A0. Just taking D1, D3, D5, D7. They are the odd values. So A0 is just the odd values. D1, D3, D5, and D7. Okay? Okay. This all about the encoder. If you have any question. Okay, I want to ask a very small question. Why there is no D0 here? Why there is no D0? There is no D0. Why? For what reason? Huh? Anybody knows? Nurhan is saying because it's all zeros. Okay, yeah, okay, I understand that you have a correct answer, but okay, I want يعني Nurhan is always sharing. I want somebody else, please. Why there is no D0?
لأن A0 الأوتبوت ماله زيرو.
الاوتبوت في A0.
أول واحد.
لا مش في اول واحد بس. ها
كلهم.
كلهم بالظبط كده. اوكي كلهم. اوكي عشان because they are all zeros. Because they are all zeros. They don't need D0. Because at this place they are all zeros, so no need for D0. No need for this D0. Okay? Okay. Thank you. Thank you who participated. Nurhan Nurhan is sharing on chat, and مين كمان؟ مين اللي اتكلمت من شوية؟
فريال.
فريال. شكرا يا فريال. شكرا نورهان. شكرا فريال.
العفو دكتور.
Multiplexers, they are an extension of the decoder, and if you see, we have four inputs: input 0, input 1, input 2, and input 3. According to the selection lines, we will get one of them as the output. It's like channel. If you see about the channel, we have which channel will be used it according to the multiplexer. So if this is 00, this channel will be go out like that. Okay. And if this is 01, this channel will be selected output. And if this is 10, or I'm sorry, this is the most S0, S1, so this is, yeah, 10, yes, and 01, this is going to be the output, and last one is 11, which is this out. Okay, just to select which one of them will get the output, which one of them will reach the output. Okay, this is the main idea of the multiplexer. I select which channel to get its output on the output terminal according to the value on the selection lines. For every 2 to the power n inputs, we need 4 inputs here, so we need 2 selection lines. If we have 8 here, so this is going to be 3. If we have 16 here, this is going to be 4 input. Okay. Yeah, it is very important, as we have seen how to select the parts inside the multiplexer is using to select which register inside the CPU. Okay, as we have seen here, the multiplexer is selecting which register to get its output to the arithmetic logic unit. And also we need it here to get the output from which one, which place, the shifter or the arithmetic logic unit. According to the multiplexer, we will get the output that we need. The structure of the two input multiplexer. If we have just two input, very simple. This is the very tiny, very small, very little multiplexer, which is we have binary selector to select which one of them will get its output to Y. For example, if this is 0, the output I0 will appear on Y. If this is 1, the output I1 will appear on Y. Take care, I0 is not logic. It is not logic now. It is just a variable of logic value. So the output here, which is I0, if it is 0, if it is 1, no problem, will appear on Y. And also for I1, if it is 0 or 1, no problem, no difference. They are appearing on Y. How this is happening? Take an example. If we have here S is 0, this means we have this branch is not working, but this branch will be working, will work. So this branch is enabled. This means the value here is 1, and the output here will depend on I0. So if I0 is 0, the output will be 0. If I0 is 1, the output will be 1. So the output will be depending on I0. Here also I0 will be passing to OR gate. We have
دكتور،
I0, yes.
يعني one في مرة بيكونوا واحدة فيهم off والتانية on، بعد كده التانية on والتانية off.
بالظبط
never
بالظبط
never both are on، صح؟ okay.
بالظبط, yes, because we have just one selection line, and the selection line has two paths. One of them is inverted and the other one is not inverted. So this way we will make sure that 100% one of them will be enabled and the other will not be enabled. I think هاجر اللي كانت بتتكلم.
أيوة دكتور هاجر.
طيب تمام يا هاجر. نيجي بقى للفاينل. Okay, I'm confused between Arabic and English, but no problem. I0 is here will be passed to the output. Why? Because as I told you, S is 0. This means this branch will be enabled and this branch will be disabled. And according to The value of I0, it will appear on the output because this is 1 and 1 and x equal x. You know that. Okay, let me write down it. 1 and, okay, let me, it's better to do it like that. 1 and x equal x. This is one of the identities that we have studied in the first lectures. So 1 and x is equal to x. So I0 and 1 equal to I0. So the output will be I0. Now we have also the output appearing to be here, and this value is 0. So the value here is 0. And we know that I0 plus 0 is equal to what? Is equal to I0. This is another identity we have studied before. So the output will be I0. Y is equal to I0. That's why we are using the selection line to enable one of them and disable the other. And accordingly, we will extend this idea to have more inputs, to have more selection lines. This is the basic one. This is the basic one. And the idea is to have a collection of ANDs, and the final one is OR gate. And according to the selection line, we will get the output and it will appear on the, for example, here, if the selection is 0, the output I0 maybe 0, maybe 0, maybe 1, maybe 1, no problem. And it will be passed to the output. It will be passed to the output because S0 is 0 means this part will be enabled and the value will be passed to the output. If it is 0, it will be 0. If it is 1, it will be 1. And if S is 1, this means this part will be enabled and that part will be disabled. And according to the value, which is I1, the output will be the same. So I1 is here, the output is the same, 0, 0, 1, 1, 0, 0, 1, 1. They are the same, the same. So I1 will appear to the output. That's the main idea. What about the 4 to 1 multiplexer? What about 4 to 1 is an extension of 1 to 2 multiplexer, or sorry, it's not 1 to 1. It is, how to say that? This is 2 to 1, yes. And this is 1 to 1, yes. This is 1 to 1 multiplexer. We call it 1 to 1 multiplexer or 2-input multiplexer. 2-input multiplexer is better because we have I0 and I1. Here we call it 4 to 1 multiplexer. We have 4 inputs and only 1 output. And the selection lines here will select which gate will be enabled. Or which gates, you can say gates, not gate, not only one gate here, because we have different values of S0 and S1. For example, if S0 here is 0, 0, okay, take an example 0, 0, and see this is going to activate D0 because this is connected, this one connected to 1, 1, and this is D0. So the output will be D0. Yes, D0 value will be passing to the output and passing to the output Y. What about the value of 0, 1? 0, 1 means D1 will be enabled. D1 will be enabled. Why? Because if you see 0, sorry, this is S1, S0, but here S0, S1. So 0 is here and 1 is here. So this is going to enable what? To enable that one. Okay. This is going to enable that one and disable the others. Okay. And the one will appear on the output. Okay, repeat it again. I told you to enable multiple gates, multiple AND gates. This is not correct. It is only one gate will be enabled at a time. One gate will
دكتور
be enabled. Yes.
ليه في الأور في الأخيرة ليه مش على طول بيطلع الواي؟
ليه ما بيطلعش الواي؟
يعني هو ليه في اور في الآخر لأنه اوريدي في بيطلع one output صح؟ يا إما دي 0 يا إما دي 1 يا إما دي 2 يا إما دي 3 مفيش بينهم حاجة ولا كلهم بيتعاملوا مع بعض اور في الآخر ويطلع واي؟
لا لازم كلهم. ما هو انت يعني انت بتتكلمي على اوتبوت واحد فقط. If you are
بالظبط.
talking about يعني if you are talking about D1 to appear on this line, it's okay. There is no need for OR gate. But the
أيوة
others
يعني لو أنا
will,
عايزة دي 0 عادي بدون اور، لو أنا عايزة دي 1 بدون اور، بس لو عايزاهم كلهم one output بعمل الأور بينهم صح كده؟
بالظبط كده.
أوكي.
تمام. يعني انا قصدي من غير الاور انت هتشغلي طرف واحد فقط، لكن عشان الاور دي مهمه جدا عشان كله يشتغل. يعني الاوتبوت لو طلع هنا هتبقى الواي هي دي الاوتبوت، لكن لو ما فيش اور يبقى انا بشتغل على حاجه واحده بس. يعني هيبقى عندي 4 لاينز مش 1 لاين. انا عايز 1 لاين بس يطلع، يعني انا عايز الداتا دي تطلع على 1 لاين. فلو شلنا الاور هيبقى عندي 4 لاينز. انا مش عايز 4 لاينز، انا عايز 1 لاين بس. فعشان كده لازم احط الاور.
أوكي دكتور.
Okay, تمام. Okay, so we have 0 1, so one gate at a time will be enabled and the others will be disabled. As we have seen the two examples here, 0 0. The output will be, this gate will be enabled and D0 will appear at the output. And for 0 1, the output D1 will appear at the output. Uh, what about 2 by 4? It's quad 2 by 4 line multiplexer. You can say it's like enabled. We have selection here to select one of these two inputs. Okay. You can say it is 4 by 1. This is 4 by 1. Two copies of the 4 by 1. This is the first copy of 4 by 1. And this is the second copy of 4 by 1. And the selection line here is, sorry, the selection line here is used to enable one of those, to enable that part or that part. If you see the selection line here, just to enable that part or that part, because the selection line is passed to this part without conversion and passed to that part with inversion. This means it either enable that part or that part. One of those two parts will be enabled at a time. This means we have A0, A1, A2, A3 will be enabled at one time, and the other time will have B0, B1, B2, B3 will be enabled at other time. Okay, and the enable signal is just to enable both of them. If I want them to be enabled to pass the output to Y01, Y2, Y01, Y1, Y2, Y3, I will enable or activate them using this enable signal. Okay. Okay. Select A. Here, I want to say something, but I forget to tell you. Hmm. To 4 lines. Okay. Okay, I just want to mention something, but I forget to tell you about. I will tell you maybe next lecture about this circuit. Okay, I forget it really. But anyway, we move to multiplexers. the logic implementation. We can also use multiplexers to make logic implementation. If we want to implement any logic, we can use multiplexers to help us do that. So for example, if we have this very simple function, which is f of a and b equal m0 plus m2. So we have a complement, b complement, which is min term 0, and a b complement, which is m2. This is just a simple function. And the function will be here. So this is a complement, b complement, and this is a b complement. This is the function representation. And I want to select the output y to be the two min terms here, the a dash, b dash, and a b dash. The idea is very simple. I want to enable the corresponding AND gate. If I want to enable, for example, here, I will show you by notation. I want to enable M0. So I enable this one, and I want to enable this one, which is M2. I enable this one. So I connect this to, I connect this to one, logic one, and I connecting this to logic one. And this is, this is too big one. This is 1, and this is 0. This is 0. Okay. I connect this is to 0, connected to 0, and I connected it to 0, and this to 1, and this to 1. Okay. And this way, okay, D0 will be, and yes, according to S0 and S1, which is 0, 0 here. Okay, let me try a combination to make sure this is working or not. If we have this is 0, 0, the output should be 1. So this one will be, this one will
1
be
1 0, huh?
this will be enabled, right? This one will be enabled, and the output will be 1. The output will be 1. Okay, so what about 0 1? 0 1. 0 1 means this one. Okay, let me clean. What about 0 1? Sorry, 0 1. Okay, if this 0 1, this means this one will be enabled. If this one is enabled, and the output will be 0, so y will be 0. Okay, you understand it? If this is 1 1, okay, last one, let me see it. If this is 1 1, this means this one will be enabled, and the output will be 0. So I make a truth table this way. You understand it? Anybody have a question about this circuit? Again, I want to implement the function f of a and b equal to m0 plus m2. The way is very simple. The method is very simple. It's just to connect the corresponding D lines with 1 or 0 according to the function. So here D0 will be connected to 1, D1 will be connected to 0, D2 will be connected to 1, and D3 will be connected to 0. And according to this, A and B will be the selection lines. A and B will be the selection lines. So the logic will be represented at the output Y. Okay.
Decoders always 1 0 1 0.
Yes, you mean
circuit.
the F? You mean
Yes.
F? Yes.
No, I mean D0
دكتور لا
D1.
بيعتمد على الفانكشن اللي عندنا صح؟
ايوه بيعتمد على
ممكن
الفانكشن.
تغير الفانكشن.
ممكن نغير الفانكشن، فاحنا هنوصل الاطراف اللي هي دي 0 دي 1 دي 2 بارقام تانية لو في فانكشن تاني.
دكتور نزيل وين الفانكشن اللي على يمين تيبل؟
لا اللي على اليمين دي
الاكزامبل
بتاع
اللي فوق
الديكودر.
اه
اللي على اليمين دي بتاع الديكودر، لكن اللي على الشمال هي الفانكشن اللي احنا عايزين نعملها. تمام.
تمام دكتور.
طيب الاسهل الديكودر. لو انتوا فاكرين الديكودر كان سهل، احنا بنوصل باور جيت وخلاص. تمام. لكن دي فيها يعني شويه، انا اتمنى ان انتوا تكونوا فهمتوها يعني. هي دايركت يعني
فهمناها
هي.
دكتور، حلوة.
طيب احنا هنوصل على طول بالايه we connect the function values. okay. M3 is M3.
بيكون 8 صح؟
لو احنا هنزود M3 يعني ولا ايه؟ نورهان بتسأل بتقول if M3.
دكتور بتقولي يعني لو في واحدة زيادة، لو في كمان بلس M3 هيبقى ليها فانكشن تانية، هو هيدينا برضو صح؟
لا لو في M3 يعني ايه؟ يعني كده لو عملناه كده
يعني M0 بلس M2 بلس M3
ايوه.
وتحت يعني ال M3 ليها بقى حاجة تانية وهو مثلا
لا
A
مش
داش
هيبقى
B.
لها حاجة تانية، هيبقى ده واحد بس، ده هيبقى واحد.
طب ليه دكتور؟
ما هو ده M3، ما ده M3، ده M3 اللي هو AB. تمام.
ايوه يعني هاي ال A M0 M1 M2 M3 ونحن الحين نسوي اول واحد واخر واحد.
لا احنا لو
اول
عايزين
واحد
الفانكشن،
والثاني ثالث واحد.
لو عايزين الفانكشن دي تبقى M0 M2 M3، فاحنا هنحط واحد عند كل واحدة من دول. هنحط واحد هنا وواحد هنا وواحد هنا. خلاص.
ايوه
وبعدين
فهمت
نوصل
دكتور.
دكتور أيوة
للوحايد
دول
دي.
ال1 only we only put a 1، يعني اللي ادينا function M0 هو ال1 و M2 هو ال1، الريست are zeros صح كده؟
ايوه بالظبط.
اوكي.
يعني المين تيرم هيبقى قصاده واحد، المين تيرم اللي احنا عايزينه هيبقى قصاده واحد، والمين تيرمز اللي احنا مش عايزينها هيبقى قصادها زيرو. تمام. اوكي. Okay, let's move to and AB will be S0 S1. Okay, if you don't understand the previous example, this is another example. This is another function. This way we'll not use 2 by 4 or 2 by 4 by 1 multiplexer. We are going to use this one, is bigger, which is 8 by 1. This one, multiplexer, 8 by 1 multiplexer. And this way we will connect this one to this terminal. We will connect it to 1, and this terminal will be connected to 2, and 0 will be connected to, and so on. We just connect, 0 means ground, and 1 means connected to the voltage source. So it is very simple. We connect the ground to the I1 to ground and I0 to voltage source or to high voltage. Okay, and then this to low voltage, high voltage, low, high. Okay, and the output. Okay, the output will be according to the selection lines, will be representing the input variables. So if the input is 0, 0, 0, the output will be 1. If the input is 0, 0, 1, the output will be 0, and so on. Okay. Another way of representing the logic gates using the multiplexer. As you know, this multiplexer is, you can say, redundant, has huge logic, but used in creating very simple circuit. How to optimize the 8 by 1 multiplexer? We can use 4 by 1 multiplexer instead. We will implement the same function here. Our objective is to implement this function. We already implemented it, as you see here. We already implemented it. So this multiplexer represents this function. But this is redundant logic. It is very huge multiplexer compared to the logic needed. We can use only 4x1 multiplexer to represent the logic, the same logic here. We want to represent this function. We can use 4x1 multiplexer and only one 4x1 multiplexer to represent the same logic. It's like half of the price. So it is 8x1. If this is $10, I will use only $5. So it is too optimized, too efficient. Okay, how to use it? Just concentrate on this part. If we have A, B, and C, this is A, B, and C here, and the function, we can use A and B. We have only 4x1. This has two selection lines. 4x1 has two selection lines, which is A, B. And the other one is C. We'll not take C exactly. We will take the complement. We will look at the function. We want the function to be 0 and 1 in this part, or 1 and 0 in this part. And when A, B is 0, I want the function to be 1, 0. When A, B is 0, 1, I want function to be 1, 0. And when A, B is 1, 0, I want the function to be 0, all 0. And when A, B is 1, 1, I want the function to be 1. Okay? Now,
Doctor, this is even?
Even? لا انا بس بعمل ريبريزنتيشن
ولا نحن
للفانكشن دي
بنسوي
اللي هي M0 M2 M6 M7.
هي اوكي فهمت.
اوكي فانا حطيت M0 هنا. I put M0 here, I put M2 here, and I put M6 here and M7 here. بعدين I look at the input, which is A, B. Okay, and look at the output, the third variable, which is C. Okay, and okay, let me explain it by the figure. It's like having the third variable or the input not exactly 1 and 0, but a function of a function of f. Okay, we return back again. We return back again here. If you look at this function, f is 1, 0, c is 0, 1. This means I am inverting c. I am inverting c. Okay, because 0 is inverted to 1 and 1 is inverted to 0. So this is an inversion. And this is when AB 0, 0. When AB 0, 1, I'm doing the same. I'm inverting C. When AB 1, 0, I'm taking 0, irrespective of the value of C. There is no, this is, C is like, don't care. I don't care about the value of C. I always get 0. And when AB is 1, I always get 1. Okay? Now I can represent the same thing using C. I can represent the function using C. So I will say the function will be, which is the input here, to be C complement, because I am complementing C. Here is C complement, and here is 0 always, because this is always 0, and here is 1 always. This means I can use the 4x1 multiplexer, and the third variable, which is C, is passed to the input one time complemented and another time complemented, and value fixed at 0 and value fixed as 1 at 1. Okay, you understand this part? يعني
Yes, doctor.
okay, أنا بس بحاول أستخدم I'm trying to use أنا بحاول أستخدم بدل ما أستخدم 8 في 1 بستخدم 4 في 1 بس باخد الفاريبل الاخير بدل ما يبقى مباشر كده بالفاليوز تبقى مباشر بالشكل ده، لا انا باخدها فانكشن في الفاريبل الثالث. I'll say it again in English. I want to optimize the use of 8x1 multiplexer just to use very small or smaller 4x1 multiplexer, not directly have an input like that, but instead I have the input as a function of the third variable. Okay, so this is the idea, just to have the input not directly zeros and one, but a function of the third variable. Okay, demultiplexers. The demultiplexers, they are the opposite of multiplexers. They have the input and one, this is the inputs S0, S1, and we will enable only one value at the output. Okay, the idea is very simple, just to have one value at the output. So if this is 0, 0, so this is D1, D0 will be active. If this is 1, 0, this D1 will be active, and so on. This is the demultiplexer. And the last thing, if you need a break, or we can continue, and I think we will not take too much time, about 20 minutes, okay? And then we will finish the entire lecture. There is no need to have a break, okay?
اوكي دكتور.
Okay. Okay, so priority encoders. If we look at the encoders, we will see that one input is active at a time. If you remember the encoders, just to know that one input is active at a time. But in case we have two input is active at a time, what will be happening? This is one active at a time, but if we have two input at a time is active, as you see here, if they are both active, D0, you have here the corresponding diagram of the encoders. And if we have D6 and D3 is active at a time, the same time, it's not allowed, but if they are active, what we will do, we will select D0 or D6. I want to know which one will I choose. I choose this one or that one. This is a confuse, this is a problem. Because the output will be 1, 1, 1, and always will be like that. If two input at a time is active, the output will be directed to 1, 1, 1. If any two inputs are 1, this is going to give us 1, 1, 1 always. I don't know that. I don't want this behavior. This behavior is not needed. I want to have a solution for this problem. Okay, I will say problem again. You know, the encoder, in the encoder, we have one active line at a time. We cannot have two lines active at a time. But if we have, for example, D3 and D6, this is going to give us the output as 1, 1, 1. But I don't want the output to be 1, 1, 1. I want to select which one to prioritize in English, like that. Prioritize. How to do this priority? How to do this priority? I want to select one of them, D6 or D3. One of them, not both of them. So I want to choose the one with the highest priority. Okay. I want to do that using this logic, which is this way. If we have D0, D2, D1, and this D0 is active, so D0 will have the priority. And
دكتور بس سؤال.
yes.
كيف نعرف ان هذا اكتف؟
اكتف يعني لا، هو احنا هنعرف ان هو اكتف ازاي؟ يعني احنا بنحط 0 او 1، يعني احنا بنحط هنا الانبوت يا اما 0 يا اما 1. لو 0 يبقى مش اكتف، لو 1 يبقى اكتف. يعني احنا اللي بنحط الفاليوز دي على الانبوت. لو
أيوة
حطينا
أنت لا.
بقى، لو حطينا 2 انبوت بواحد هيبقى في مشكله، لان
صحيح.
احنا مش عايزين الاثنين انبوت يكونوا بواحد، احنا عايزين واحد بس يكون بواحد. عشان كده لازم نحل المشكله دي. فهنعمل حاجه اسمها البرايورتي، الاولويه، مين اللي ليه الاولويه. فاحنا هنشوف، هنعمل حاجه او هنعمل دايره جديده للانكودر بيكون فيها الاولويه. تمام. فالبرايورتي يعني here we have D0 D3 D2 D1 D0 this way. The output will be 0 0, and here we want D1 to be having a higher priority on over D0. This way, I will give D1 the priority irrespective of the value of D0. And here, I will give D2 the priority over the other two inputs irrespective of the value D1 and D0. And the last one, I'm giving D3 the priority over D2, D1, D0, irrespective of their values. Okay, this is the idea. The truth table will be like that. This is an extension of the truth table actually. And we have here 0 0. We have the output. So this is 0 0 0 1. The output will be 0 0. Here we have, we will take two values of D0. One at D0 is 0. The other is 1. Because it is X means it has two values, 0 and 1, 0 and 1. So I study that both cases. And in all cases, A0 will be active. Okay. And the value, the output value will be 1, which is 0 1. This is the output value is 0. This is the output value will be 1. So it will be always 1, irrespective of the value of D0. What if all inputs are 0? What if all inputs are 0? This way, I have to solve the problem using another output. This output is called the valid output. I have to check the validity of the output. So if we have an input all zeros, if it is all zeros, this means we have a variable which is V, it will be 0. This means it is not valid input. And irrespective of the value A1, A0, it's XX, irrespective of it, the validation will be, I mean, the circuit will not be valid, or the output will not be valid. And here, any other combination is okay because the output will be valid. The output will be of the valid variable will be 1. This means it is valid. Okay. And this is the expanded truth table that we have studied here. This one. That one. We started only by 3 entries. It is extended because this one will have 2 variables because either 0 or 1. But here we will have 4 variables. So you can say 1 2 و3 1 وهنا في 2 وهنا في 2 يبقى في 3 وهنا في 4 يبقى فيه 3 و4 يعني 7 وبعدين في here 8 plus 7 is 15. So the output will be 15 entries. This is 15 entries. And yes, we don't care about the valid. Yes, it is not represented here. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. Yes, okay, so they are 15. اه yes هو ضاف كمان yeah he added also the valid the 00 yes he added also 0000 so the total is 50, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 so they are 16 because he added the all zeros entries here. So it's correct. So all the entries here in the table, we have to make the Karnoff map for it. D is 3, D2, D1, D0, D3, D2, D1, D0, and the output A0 will be represented here. And we can have all of these together, these two together, and the output will be D3 plus D2 complement D1, which can be represented by this very simple circuit. This is the priority encoder. This is the priority encoder. This is the implementation of the priority encoder. I just want you not to cut you are doing. I want to make priority encoder. I started by um, expecting multiple input to be one. Then I said uh, I have to solve it using the priority. So I put don't care for the other terminals. If one of them is one, the others will be ignored. And I said, if I have all zero input, what will I do? I said I will have a valid input. Then I make the truth table of the all of the inputs, and then I start to make the Karnoff map, and finally I implemented the priority encoder. This is the priority encoder, including the valid output. This is the priority encoder, okay? And this is the end of this lecture. If you have any question.